All right, so we're going to go over some of these questions from Chapter 6, the Chapter 6 quiz. I have here the first question. Potassium iodide into atoms of potassium iodide. So the first step in this question is really to identify what potassium iodide is. So just looking it up on the periodic table, it should be Ki. We know that it's a single potassium and a single iodine because potassium is in the first column of the periodic table. So it has a +1 charge. And iodine has a -1 charge because it's in column 17 or 7a. And so it's a -1. This is important because we have an ionic compound, which you know because the first element in the compound is a metal. So most of the periodic table is metals. So in our ionic compounds, the charges have to balance. So that's the first step. And then we want to calculate then the molecular weight or the molecular mass for potassium iodide. So I've already gone ahead and looked up the molecular masses for the individual atoms. So for potassium, it's 39.098. 39.098, just typing it into my calculator, plus 126.90. So our molecular weight for potassium iodide is going to be, so for Ki, it's going to be 165.998. You want to make sure that you include all of those decimal places, otherwise you can get rounding error. I did notice some people got that on this. Okay. So the other concept that we're exploring here is the fact that everything is made up of atoms. And we can calculate using the molecular weight or molecular mass how many atoms make up anything as long as we know its mass. So we have 25.4 grams of potassium iodide. So take our 25.4 grams of Ki. And this is, we start with this number because this is the quantity that we're given of a thing. This is going to be our conversion factor. It's a conversion factor because it's 165.998 grams per mole. So per means division, so it's grams per mole. So we want to convert from grams, because we have grams here. Right? We're working with grams of potassium iodide. We want to go to moles, because moles is really, it's an easier way of counting a number of atoms. So to do this, we're going to take 165.998 grams per 1 mole. Sorry, these are both potassium iodide. Grams of potassium iodide. Goodness gracious. Potassium iodide per 1 mole of potassium iodide. So when we multiply these, potassium iodide is going to, or grams of potassium iodide is going to cancel out with grams of potassium iodide, and we'll be left with what we're looking for, or at least the next step in what we're looking for, is moles of potassium iodide. So, use on the calculator, 25.4 divided by 165.998. And that's going to give us 0.15301,389. And you want to have all of these in here. So now we've got moles potassium iodide. So the next step then is to go from moles potassium iodide to atoms of potassium iodide. To convert between moles and atoms, it's 6.022 times 10 to the 23 atoms is equal to 1 mole. Or we could say 6.022 times 10 to the 23 atoms per mole. So now when we set this up, we want to convert from our 0.153 0.01389 moles of Ki. And because we have, again, we have moles here, we're going to want in our conversion factor then, we're going to want moles on the bottom to cancel this out. So the way that we have this written here already to convert between moles and atoms, we're already going to have one, probably wrote this in kind of the wrong spot, but moles potassium iodide, and 6.022 times 10 to the 23 atoms. Actually, this can be moles of potassium iodide, but really it's just moles. We're canceling the moles and replacing moles with atoms. I ran out of space here, so I'm just going to write it down over there. So I'm going to do our 0.153, right, long number, and I'm going to multiply that by 6.022 times 10 to the 23. So our final answer here should be 9.21 times 10 to the 22 atoms of potassium iodide. Okay, for number 2, we had convert 10.8 grams of sodium carbonate into atoms of sodium carbonate. So very much doing the same sort of question here. The next level, though, sort of, in that you need to now, you're given the symbols or the molecular formula for sodium carbonate, and now you need to calculate its molecular weight. I went back and corrected this. I made a mistake when I calculated the mass of sodium carbonate, the molecular weight. I corrected those, and anybody who did actually get it right, but the wrong answer was looking for the wrong answer, I fixed those. But when you do this, again, I've already gone ahead and looked up these values from the periodic table. And so we've got sodium, carbon, oxygen. And what you need to do with these is multiply each by the number of atoms that are in your molecular formula. So 2 of those, we only have 1 carbon. So you think about multiplying by 1, but you don't really need to. I'll write it in here, right? Multiply by 1, multiply by 3. So these numbers that I'm multiplying by are coming from the periodic table. And once you get each of these numbers, you'll add those together. And I've already done this little bit of math ahead of time. Should be about 105.98 grams per mole. Now, your answer here might vary a little bit simply because of the periodic table that you're using. I'm using right now ptable.com, which I think gives more significant figures than the periodic table in the book. But the periodic table in the book is always a good one to go to, and I try to account for small differences in the way that the Canvas is looking for the answer. So this problem, again, very much the same. And on this one, I'll just go ahead and do a little sort of solution diagram. So again, you want to look for these values that are just sort of given, as opposed to those values which are conversion factors. So, right, this is grams per mole. That's a conversion factor. This is just 10.8 grams of sodium carbonate. So then we are going to start with that 10.8 grams. So we're starting with a value in grams. And then we need to convert first to moles. The reason that we need to convert to moles first is that's kind of the conversion factor that we're able to get to easily. So grams, we want to get to moles. We can see that molecular weight is in those units of grams per mole, right? So it has where we're starting and it has where we're going. Whoops. And so this also kind of requires the knowledge that from moles, it's easy to go to atoms, because our other conversion factor is 6.022 times 10 to the 23 atoms per mole, or 6.022. This is exactly the same thing, just written a little bit differently. Atoms per 1 mole. Okay, so then at this point, we just kind of plug in our numbers. We say 10.8 grams, Na2CO3. We're going to use the molecular weight of sodium carbonate. And again, when we're going from grams to moles, you're going to divide by your molecular weight. So it's grams of sodium carbonate. It's always good to write out all of your units for 1 mole Na2CO3. And then to go from moles now to atoms, we'll just use our next conversion factor, which is this one up here, right? Again, and we'll look at this, right? So we're going to end up here with moles, and we want to get to atoms, which we have in our prompt. So we want to go from moles to atoms, from moles to atoms. When we're starting out, we have grams, and we want to go to moles. So this is how these solution diagrams can be helpful when you're trying to identify which conversion factor to use next. So here we want to go from moles, and we want to end up with atoms. So we're going to put the one that we want to end up with on top. We're going to end up with it on top. So 6.022 times 10 to the 23 atoms. And that'll be atoms of sodium carbonate. It's wordy, it's a lot of stuff to write out, but it helps you stay on track. And this is going to be per 1 mole sodium carbonate. When you're doing these conversion factors and you're using Avogadro's number here, it's always like atoms to moles, and then whatever you're converting from, you can add here at the end as well, right? Because we're going to still end up with sodium carbonate, but it can help a little bit for clarity's sake. And so again, I've run out of space. What I'm going to do are 10.08. I'm going to divide by 105.98. Oops, 105.98. And then I'm going to multiply by 6.022 times 10 to the 23. So our final answer will be 6.14 times 10 to the 22 atoms. Keep giving myself not enough space, but atoms of sodium carbonate. And just, I think I forgot to mention this on the first one, but the reason that I'm using 3 sig figs here is because we had 3 sig figs up top in our prompt, and this is the only number that we're given, and all of our conversion factors have more sig figs. Sorry, this is 5, 1, 2, 3, 4, 5. This is 1, 2, 3, 4. We have more sig figs in our conversion factors, and in general, the conversion factors aren't going to change your number of sig figs. So that's how we get the answer for number 2. So for this next problem, number 3, I wanted to test your concept or your knowledge on a different concept, really. So we want the atoms now of just hydrogen in, this is methyl bromide. And the relationship between atoms and moles, I mean, when we're using atoms or moles, we're counting individual atoms. So to say 13.2 moles, that's just a number of atoms. And it's a really, really big number of atoms. But then for each methyl bromide molecule, we have different numbers of individual atoms that are attached together, because that's what molecules are. They're atoms all attached together. So the concept here is that, and it doesn't really matter for this what orientation they're attached in, but let's say you have a carbon atom. Let's just say everything's attached to the carbon atom. We got a bromine over here, and then these other 3 are hydrogen atoms. So when we have these hydrogen atoms, for each one of these methyl bromide molecules, these CH3Br molecules, how many hydrogens do we have? So let's do it like this. Let's say if we have 1 CH3 Br molecule, how many hydrogens do we have? Take a guess. I'll pause here for a little bit. You can pause the video if you want to. We're going to have 3 hydrogens. So if you look at this, right, so there's one whole molecule, and then there's 3 hydrogens inside of that molecule. So it's kind of like how a car, right? If you have one car, that one car has 4 wheels. So if we take this and we say then now, okay, well, what about in 2 CH3 Br molecules? How many hydrogens do we have then? We can just say that, oh, we take 2 and multiply it by the number of hydrogens. So we have 6 hydrogens. You can think about it too, and maybe I'll write this parallel. So one car, how many wheels? And we're not counting the steering wheel. How many, rubber wheels on the road does it have? And there are weird ones out there, but in general, right, 4 wheels. If we have 2 cars, how many wheels do we have? 8 wheels. So it's a very similar thing. So let's scale this up even farther now. So what if we had 1,000 methyl bromide molecules? How many hydrogen atoms do we have? Again, you can just take 1,000, multiply it by our number of hydrogens, which is 3, and we have 3,000 hydrogen atoms. So let's go now to sort of the scale that we're working at. Let's say we have 1 mole of CH3Br molecules. How many methyl bromide, or sorry, how many hydrogen atoms do we have? Well, it would be a lot to say how many individual hydrogen atoms we have, so let's just work in terms of moles. So let's say we just take our 1 mole, oops, meant to use this guy, 1 mole, multiply it by 3 hydrogens, we have 3 moles of hydrogen atoms. So when you're given a question that asks you for the number of atoms that are in a molecule, right? How many atoms of hydrogen are in this molecule? You can just look at the molecular formula to get the number of atoms and multiply the number of moles that you have, or the number of atoms, by the number of atoms that are in an individual molecule. So we can take our 13.2 moles. With this is in mind now, I'm going to just scroll down here and we're going to work from here. So we got 13.2 moles of CH3Br. And let's make a little conversion factor here too. And we can actually use this guy that we were just working with. So let me highlight that to show that we're working with it. Use orange, that's a different color. So we have 3 moles of hydrogen atoms per 1 mole of CH3Br atoms. So we can write 3 moles of hydrogen per, right? So this line means per 1 mole of CH3Br. And now we have our conversion factor. And actually, let me move this as well. So maybe we got a little bit ahead of ourselves. We're going to start with moles, and we're going to move to, or actually, even more so than this, we're going to start with moles of CH3Br. And then we're going to go to moles of just hydrogen. And then we can go to atoms of hydrogen. So, if we have, I'll just move this, right, 13.2 moles. We just came up with this conversion factor. So we can do 3 moles of hydrogen divided by 1 mole of CH3Br. So we'll just take our 13.2 and multiply by 3. That'll be 39.6 moles of hydrogen. And now we want to go to just individual atoms. So we're going to convert this mole to atoms. And to do that, like on all these other ones that we've been doing, we go 6.022 times 10 to the 23 atoms is 1 mole. So if we take our 39.6 times 6.022 times 10 to the 23, we will get, round to space again, 2.384, I'm just going to write this out, times 10 to the 25 atoms of hydrogen. So how many sig figs should we have, though, for our final answer? Let's look at all the numbers we've been talking about here, because we've kind of gone through a lot of the numbers on this one. But even just looking at our initial here, we were only given 13.2. So that's going to be 1, 2, 3 sig figs. So if we come down, everything else that we've used up till this point is a conversion factor, this is just an intermediate step. So then we need 3 significant figures on our final answer for 2.38 times 10 to the 25 atoms of hydrogen. So that's number 3. Covered a lot of stuff in between there, but that's number 3. All right, so now we're on number 4. If a sample of sulfuric acid has 4.76 times 10 to the 34 atoms of sulfur, how many kilograms of sulfuric acid are there? I think at this point, it's good to write out, and this is not specific to this problem, but really is in general for all of these problems. We always go from grams. If we have grams, or really, any other unit like grams, kilograms, we just use kilograms or grams, but if we have any other unit of mass, so we have pounds, if we had ounces, if we have milligrams, we always go from those mass units. And we go from those mass units to grams, if we're ever concerned about atoms or moles. And once you get to grams, the reason grams are so convenient is because our molecular weight or molecular mass is in units of grams per mole. So that's our molecular mass. Those are the numbers on the periodic table. And you can count these, so the molecular mass then is the mass of a molecule. So in this case, sulfuric acid. I wrote it as sulfuric acid to make you go and either look up what sulfuric acid is or test to see if you know what sulfuric acid is. So in this case, it's H2SO4. You can go back and review nomenclature for how to get that. It's one of those things that you can memorize, or from the nomenclature you can figure it out as well. So the molecular mass for these things we can use to go from grams to moles. So it's kind of moving with units that we use to weigh things out, to get the mass of things, and then also then into the sort of realm of atoms and molecules. So from grams we would go down to moles. And then for moles, we can use Avogadro's number, 6.022 times 10 to the 23, down to atoms. Oops, made this box too small. And then from atoms, like in this problem, if we're given atoms, we can go back up to moles. We go back up to grams. Again, to go from atoms to moles, that's Avogadro's number. That's a 6.022 times 10 to the 23. And then from moles to grams, that's where we use our molecular mass to do that calculation. And once we're in grams, we can do any of these other mass units pretty easily by converting. So if you're on one side or the other, and there's a reason that I sort of wrote this this way, in this mirrored sort of fashion. If we have any sort of mass unit, we can go all the way down to moles to atoms, and then from atoms, we can go up from moles to grams to what other mass units. So it works in both directions. In this problem, we're going to be starting with atoms, and we want to go to kilograms, which you'll notice is in this list of other mass units. But it's easy to go from grams to kilograms. So then our solution diagram for this is going to be atoms to moles to grams and then to kilograms. Got these little boxes. So that's going to be our solution diagram. I did not get the masses of these beforehand. So our sulfuric acid, we're going to need the molecular weight for that. I'll do that on the right side. So we have hydrogen, and we have sulfur, and we have oxygen. Our mass for hydrogen, according to the periodic table that I'm using, is 1.008. That's grams per mole. Sulfur is 32.06 grams per mole. And oxygen, 15.999 grams per mole. And then we just take each of those masses and we're going to multiply it by the number of those elements in our molecule. So for hydrogen, it's 2. For sulfur, it's 1. For oxygen is 4. Because here we have 2 hydrogens. There's no subscript. That's what these smaller numbers are. They're subscripts. There's no subscript for sulfur, so it's an implied 1, because otherwise why would it be written here? And then for oxygen, it's 4. Let me grab my calculator. So 1.008 times 2 plus 32.06, 32.06 times 1. Oh, I messed it up. 1.008 times 2. Plus, I'm just going to add 32.06, because that's the same as multiplying by 1, then adding it. And then I'm going to add 15.999 times 4. So our molecular weight, or molecular mass, is going to be for, wrong one. H2SO4 will be 98.072 grams per mole. Okay, now that we've gotten our molecular weight, which is not always necessary, if you notice that going from moles to atoms, we don't need molecular weight. Or if we go from moles to atoms or atoms to moles, either way, we don't need molecular weight. Okay. Now we have, now we can start filling in this table. And again, we're starting with atoms because that is not a unit per something. There are some cases where, if you're given nothing else, if you're only given stuff that has per units, so if you're trying to do miles per gallon or grams per cubic centimeter or grams per mil, those are some of the exceptions to always being a conversion factor, although they can also be used as conversion factors. Sorry, that's a tangent. So we're starting with atoms because this is actually our only given unit here. So it's going to be 4.76 times 10 to the 34. I'm going to write the units underneath it. Atoms of H2SO4. And so we want to go from atoms to moles. So in every problem we've done up till this point, we've been doing the other way around, going from moles to atoms. But when you go from atoms to moles, we're now going to divide by 6.022 times 10 to the 23. This is atoms. This is 1 mole. So we'll divide by that. And then we want to go from moles to grams. So we'll take, and looking at this over here, right, we got grams per mole in our molecular mass. And so we'll do 98.072 grams per 1 mole. And you'll see that we have grams on top, and grams is the unit that we want to end up with based on our solution diagram. And then to go from grams to kilograms, you need to know that 1 kilogram is equal to 1,000 grams. So the unit that we want will go on top, 1 kilogram. This is true for converting units in the numerator. So the numerator is this top number. So if we're converting the top number, we put the new unit that we want where we want it to be on top. So then we're going to divide them by 1,000 grams. So plug this into the calculator. 4.76 times 10 to the 34, big number, divided by 6.022 times 10 to the 23. And then we're going to multiply that by 98.072. So that's our molecular mass of sulfuric acid. And then we'll divide that by 1,000 to get our final answer of 7 point, and again, thinking about significant figures, we only have 3 significant figures here. Whoops. 3 significant figures here. So we're going to have 7.75 times 10 to the 9 kilograms of H2SO4. So that is problem number 4 from the Chapter 6 quiz. Okay, final question I'm going to go over, or I'll tag on maybe a brief statement about the other 2 sig fig problems. If the average caramel macchiato has a mass percentage of 11.1%, how many grams of sugar are in a venti? 20 ounces. So that's actually 20 fluid ounces. Let me know if you did that problem differently. So the density of a caramel macchiato were given as 1.16 grams per mil, and that number was set to change along with the percentage. So if you have a different number, don't worry. And then you're given that 1 fluid ounce is equal to 29.5735 milliliters. And I gave you this many significant figures because it shouldn't affect your final number of significant figures. So the first thing you need to do for a problem like this is, again, set up a solution diagram, especially for a problem like this. We're given mass percent. Oops. We're given mass percent. Mass percent is the proportion of the whole that, in this case, sugar is. So the proportion of an entire caramel macchiato that our sugar is. So it would be, to convert this to the proportion, we would go from, so if we want percent to proportion, we're going to go 11.1%, and then we're going to divide by 100 to get 0.111. And this is a mass percent. So this is 0.11 grams of sugar per 1 gram, in this case, caramel macchiato. And I'm definitely not gonna write that out every time. Okay, so, right, we need to convert this to a proportion. And when we convert it to a proportion, now you can see this is an amount of sugar or a mass of sugar per a mass of caramel macchiato. This is a conversion factor. So the number that we're given that's not a conversion factor is this 20 ounces. So we're starting with fluid ounces because we want to know how much sugar is in this average sort of caramel macchiato. Okay, so now we've got fluid ounces, and we're given a couple other conversion factors, like I mentioned. This is the conversion between fluid ounces and milliliters. We're given then also the density of a caramel macchiato. So I'm sort of testing your knowledge about density here as well. So we're starting with fluid ounces. We've been given this conversion factor. We've been given this conversion factor. And we've been given this conversion factor. This problem is actually, because of this, pretty convenient, because we can look at what we're starting with, fluid ounces, and we see that we have a conversion factor that goes from fluid ounces to milliliters. And then we can go from milliliters to grams. So this is grams of total caramel macchiato. And then we can use grams of caramel macchiato to go to grams of sugar. So we've got sort of given to us a flow through this problem step by step. And that's one of the things that I look for when I do these kinds of problems. And especially if I know, like if I'm given something like imperial, you're almost always going to be going back to metric. So you might look at your chart of conversion factors and say, okay, what conversion factor do I have that will take me from fluid ounces back to metric? And then write that down. And then once you have a way into metric, you're going to say, okay, well, I'm converting from fluid ounces into milliliters. I need to go now from milliliters. I'm going to get eventually to grams. In this problem, we're given the density. And density is generally, if not always, the way that you go from milliliters to grams, or the other way around. And so these are kind of the things that you need to know that we've been building up to, at least in the lectures, and these like bits of knowledge that you keep having to go back to and stack on top of to do these later and later problems. And this is a good example of a problem that I will put on exams. It tests a lot of different concepts in a single question. So we know now we're going to go from fluid ounces and we're going to go to milliliters. So I'm just going to write, we're not going to write in the conversion factors yet. I'm just going to write out my solution diagram. From milliliters, we're going to go to grams. And this is really grams of caramel macchiato, which I'm just going to abbreviate as CM. And then we're going to go from grams of caramel macchiato to grams of sugar. And we're starting with 20 ounces. So we're going to go from 20 ounces, sorry, let me write this as fluid ounces of caramel macchiato, really. And then we're going to say, okay, the unit that we want on top, that is the unit that we're going to put on top here to multiply by. So we want to end up with milliliters on top, so we're going to multiply so that we have milliliters on top. So it's going to be 29.5735 milliliters, right? That's the unit we want. We put that on top. And then we're going to put 1 fluid ounce on the bottom. Now we've got milliliters on top, and we want to convert to grams. So we want this unit on top to be grams. So we're going to look at our density of a caramel macchiato. And we're going to say 1.16 grams per 1 mil. And after we've converted to grams of caramel macchiato, or CM caramel macchiato, now we can use this percent mass to convert to, or sorry, this is the percent mass. This is the proportion. We can use that proportion then to convert into grams of sugar. And again, you can think about it like this. We have grams of, and maybe it's important here to write CM, grams of caramel macchiato, and we want to get to grams of sugar. So the unit that we want on top is we're changing this, and we want it to be this. Or sorry, I should just highlight the units. We want the units here to match the units here, or to change the units. So we're going to put, 0.111 grams of sugar over 1 gram of caramel macchiato. So once we've written out our entire solution diagram, now we can just go back in and we can multiply. And in this case, we're just multiplying across the top. So we're going to do 20 times 29 point, and you want to use all of these digits in here, 5735. And then you may not know this, but you can just multiply by, or you don't have to hit equals every time. You can type in this case, if you're doing just multiplication and division, you can just type those in. You don't have to write it out on a piece of paper and then enter it back into the calculator. So I multiplied by 1.16. My calculator says 686.1052. Then we're going to multiply by 0.111. And we're going to end up with 76. We're going to keep in mind the correct number of sig figs. It's actually going to be 20 fluid ounces, which is ambiguous because I didn't put a decimal on there. So really, we don't know how many sig figs we're supposed to have on this one, but I think I told you to report it to 1 decimal place. So this should be 76.2 grams of sugar, which is a lot of sugar. Okay, so that is problem number 5 from the Chapter 6 quiz. I just want to look real quick. This is a problem. This problem is going to be recurring. I'm going to put this on every exam. I'm just going to say it right now. For those of you who are watching this because you actually want to learn, how many sig figs does 10 have? It's just written like this. I mean, if we get 10 grams, 10 milliliters, doesn't matter. What are the rules? The rules are non-zero numbers. Those are significant. And then zeros between non-zero numbers. And the last one is if there is a decimal then trailing, or I should say then zeros after non-zero numbers are significant. Well, that was more writing than I wanted to do. So in this case, is there a decimal place? No, there's no decimal place. So this is ambiguous. The only time this is not ambiguous is if there is a decimal place. So if this is 10 decimal grams, now we have 2 sig figs. If we have 11 grams, that's also 2 sig figs. But this 0, we do not know if it is significant or not. If you want to write it another way, you could write 1.0 times 10 to the 1. That's 2 sig figs. But you'll also notice that we have a decimal here and we have a 0 after a non-zero number. So the problem is that we don't know if this 0 is significant or not because it's not a non-zero number. And it's not a 0 between 2 non-zero numbers. And there's not a decimal. So if there's not a decimal, then it doesn't fall into any of these categories. We can't say it's 1, we can't say it's 2, and we can't say it's 3. It's none of them. which means that it's not just not significant, but we don't know because there's no rule about it, because there's no way to tell if it's significant or not. So any of these, doesn't matter how many zeros there are, doesn't matter if this is 4, 3, 4, 0, 0, 0, this is still ambiguous, and it should be written with scientific notation. Okay, I hope those helped. I hope you understand this quiz a little bit better. I'll continue to post these videos. The quiz is available so that you can continue to work on it online and retake it.